SwayamPrabha. Digital India. Educated India.
We will begin this lecture by transforming the compressible energy equation. The transformed 2D laminar compressible boundary layer equations, they of course comprise of the compressible momentum equations as well as the energy equation, and we do not explicitly invoke continuity because we have already brought in the stream function. So, we will discuss the energy equation next. Followed by that, we will discuss about skin friction and heat transfer coefficient, and also simplification of the transformed compressible laminar boundary layer equations for a flat plate, where a self similar solution will be happily possible. We recall from the last lecture that we were discussing about the x and y momentum equations, the compressible boundary layer equations in the transformed scenario, in the transformed space or plane, and in the previous lecture we had shown some details of the transformation functions to be used, how we transform the derivatives from the physical space to the computational or rather transformed space, and we had looked at the two equations thereby which were formed in the transformed space, namely the x momentum and the y momentum equations. Now, we will be looking at the energy equation. The boundary layer energy equation, if you want to transform it using the necessary transformation functions, then you have to bring in a non-dimensional static enthalpy which will play a big role here. So, it is a ratio of H by H E, where again H is dependent on the location where you are starting the flow, and H E is of course at the edge of the boundary layer. Sometimes we will be writing B L to abbreviate boundary layer. So, we define a new function g, which is that of chi and eta, and we use the transformation derivatives like we did for the x and y momentum equations, and therefore, the transformed boundary layer energy equation for a 2D compressible flow, of course, steady, laminar, etc. So, that comes to this form. You already saw this term C, and now additionally you see Prandtl number, and like we saw before, we have some derivatives like f dash, now additionally g dash, f double dash, all these are purely functions of eta, but whenever you see terms like these are derivatives with respect to xi, and it goes without saying that if you are to solve these equations, you will inevitably get non-similar boundary layer solution, though in the transformed space, because you are now solving the problem in the xi eta coordinates instead of x y coordinates. So, here it is just reiterated that we said a minute back that we are talking about non-similar boundary layer profiles if we solve the equations now at this point, because they have a dependence of both xi and eta. Now, in the transformed boundary conditions, you see how they appear at the wall. since you are solving the transformed conservation equations, you also need to have transformed boundary conditions. They cannot be the ones that you applied in the physical space. So, instead of saying y equal to 0, we now say eta equal to 0, which represents the wall. Instead of saying u equal to v equal to 0, you just state it in terms of f, which has the significance of xi carried along with it. So, both f and f dash are 0, because one stands for the stream function value, the other stands for the velocity ratio, the u by ue, both are 0. And then at the wall you can have an isothermal or an adiabatic wall boundary condition. Now, that in the transform space again looks different, because we do not talk about either temperature or enthalpy, but we talk about a non-dimensional enthalpy, which is in terms of g, the function g. So, this is the isothermal value, the GW, which is the wall value for g, while here it is the gradient of g again at the wall, which is 0 for a adiabatic wall boundary condition. At the edge of the boundary layer, where eta tends to infinity, f dash is 1 because u tends to ue, g is equal to 1 irrespective of whether you have an isothermal or adiabatic wall boundary condition. You will be asymptotically going towards a condition where h limits to He, and therefore, g will go to 1. In physical space, you would say T tending to Te instead, or even H tending to He if it is in terms of enthalpy. Now, as I said a few minutes back, that in this situation, if you attempt a solution of the conservation equations based on let us say isothermal wall boundary condition, where you have GW specified, then you will get non-similar boundary layer solution for the static enthalpy, and the static enthalpy profiles will turn out to be like this at different xi stations. So, of course, you have different stations here at which you are plotting and showing the velocity profile, or rather the enthalpy profiles, static enthalpy profiles, and they will show up like this. And you notice that there is some kind of a peak which is forming in the enthalpy profiles, and we will discuss later that this is arising out of the viscous dissipation which is operating within the boundary layer. As the flow slows from a very large free stream value to no slip condition at the wall, very large viscous dissipation occurs, and that increases the internal energy of the gas, and that reflects in enthalpy as well due to the temperature rise. And you see that H has a typical profile which peaks somewhere inside the boundary layer. Again, since it is going to be a non-similar solution, when you look at the kinematic part, the velocity distribution, it varies from station to station. It does not collapse to a single profile. Velocity and enthalpy gradients at the wall, they are given by F double dash, because F double dash has a connection with this, and in terms of the enthalpy it is G dash, and again it is depending on the streamwise station xi. It will change from station to station as long as it is a non-similar problem, but eta is equal to 0. And we are talking about the gradients at the wall. This gradient, when applied at the wall, provides the necessary condition. Further, values of these two derivatives are of primary importance, since the local skin friction coefficient, which we signify by Cf, is related to the F double dash, and the local heat transfer rate at the wall is related to G dash. And this is where the practical significance of a boundary layer calculation lies. So, after solving all these equations, the main information that we end up getting is values of these parameters f double dash and g dash at the wall. Whether it is a similar, self similar or a non similar solution, we look forward to these values. Why is it? Because one connects with a very important parameter, the local skin friction coefficient, which will determine the drag for us, the drag acting on the plate being a part of a larger vehicle and so on. The other one, the G dash, is connected with the local heat transfer rate, and therefore, that will decide the aerodynamic heating that the vehicle will encounter. To begin with, the flat plate will encounter, because we will start with a simpler geometry, though we have not addressed the flat plate problem yet specifically, but we are trying to take it forward towards that. When the transformed boundary conditions are used to solve the transformed x and y momentum equation and energy equation, the solution is in this form, the variation of velocity and enthalpy through the boundary layer. This is the variation of velocity, this is the variation of enthalpy, and see that these two functions are basically kind of weightage functions which are acting on the free stream values. So, how these functions change through the boundary layer will finally decide how the velocity or how the enthalpy changes. So, variation of these functions define how u and h respectively vary through the boundary layer. Of course, on one hand satisfying the wall boundary condition, and on the other satisfying the far field boundary condition. So, this is a term we often use in computations also, far field in the sense that it is far away from the wall, which is devoid of the viscous effects due to the boundary layer, and therefore, in our case it is like saying eta tending to infinity. Note that it effectively boils down to solving the x momentum equation and energy equation, since del p del eta equal to 0 condition which comes from the y momentum equation has already been accounted through this information, p is equal to p e, which is a function of xi. This was discussed earlier too, and we recall that the Euler equation has to step in order to give us that solution. Again, this condition holds good as long as you have m infinity at a moderate value. Only then is the pressure gradient close to 0. The continuity equation is not explicitly solved, as the mass conservation is automatically satisfied through the incorporation of stream functions. So, the moment you define stream function, the mass conservation is automatically ensured. And we recall this function for stream function. The value of h and p which are obtained through the boundary layer equation solution, and of course, also the u, it helps us to compute what? To compute temperature, density, and from equilibrium thermodynamics we know that if we know the values of two independent variables, let us say h and p in this case, then the dependent variables temperature, density, etc., can be perfectly obtained through that. And then if you look at the equation of state, you have p equal to rho r t. As mentioned earlier, f double dash and g dash values are of utmost significance to calculate the skin friction coefficient and heat transfer rate. Let us try to elaborate on that front. So, by definition, Cf is the wall shear stress by half rho e u e square, the wall shear stress being given by this relation mu times del u del y at the wall. Here of course, we are again expressing them in the physical space. They need to be transformed to the transformed space in order to be compatible with the governing equations that we are handling in that space. But for now we have reverted to the physical space to define them initially, and tau W is basically the local shear stress that we are talking about at the wall. When it comes to the heat transfer rate, you can either define it in terms of the Nusselt number, which is given by QW times x divided by Ke times TAW minus TW. We will explain the significance of these terms. The other way of specifying the heat transfer rate is to invoke the Stanton number Ch given by QW divided by rho e UE times in brackets HAW minus HW, where both Nusselt number and Stanton number contain a few terms which are common. To begin with, the most significant one, QW, it is the local heat transfer rate. So, this is basically energy per second per unit area which is being exchanged at the wall. Either the wall is getting heated from the flow or the wall is losing heat to the flow, and by definition QW is K times del T del Y at the wall, K being the thermal conductivity. What is x, which figures in the Nusselt number definition? It is the distance along the wall measured from the leading edge of the body. This is only applicable for the Nusselt number, not the Stanton number. Coming to Ke, it is the thermal conductivity at the edge of the boundary layer, and it of course depends on Te, and it is again applicable for Nu, the Nusselt number. Coming to the temperatures, the subscript AW stands for adiabatic wall, and therefore, you have temperature and enthalpy for an adiabatic wall, and just W stands for wall temperature, which could be catering to an isothermal wall. That means, you have a constant temperature or enthalpy at that wall, which is specified. Now, going for the transformation, the transformed expression for Cf will turn out like this, where you can see the emergence of the function f double dash. So, this will be available from the velocity profiles that has to be fed into the Cf expression, and thereby you should be able to calculate it in the transformed plane. And then if you look at the local heat transfer coefficients, either in terms of the Nusselt number or the Stanton number, an interesting fact about the Nusselt number comes up over here from its definition. If you rearrange them, you have a first group coming up over here, which corresponds to the Stanton number Ch, and for convenience you split the enthalpy expression in the denominator into Cp times the temperature difference, because that temperature difference relieves the Cp, and that has to be adjusted over here, so that you can bring in the Prandtl number, and in between comes the Reynolds number. So, you have a beautiful combination of non-dimensional numbers representing the Nusselt number, which basically also means that if you were to calculate Stanton number for the flow, then automatically by plugging that into this relation you can get the Nusselt number. The Stanton number in its transformed sense would show up like this, and that is easy to calculate because it contains G dash, which basically comes from the static enthalpy profiles. This is at the wall, eta equal to 0, and therefore, the slope that you have of the enthalpy profile, you may recall that these kind of enthalpy profiles were seen, and therefore, from the profile itself you can make out that there is a non-zero value of G dash, which will have to be fed in over here in order to get you the Stanton number. Now, this is a wish which we are trying to explore and see whether it comes true or not. That is, we are trying to simplify the governing equation for a flat plate, and we wish that that happens, and the wish is to the extent that we would like to see whether a self similar solution is at all possible for a flat plate or not, where the problem, instead of being dependent dependent on xi and eta, becomes purely dependent on eta, if it is possible. For inviscid flow over a flat plate, where there is no influence of the displacement thickness of the boundary layer, obviously the UE will remain constant. Similarly, T, rho E, all these are going to remain constant. The wall boundary conditions, either in isothermal or adiabatic sense, will be like this, and under the above conditions, the x and y momentum equations, or rather the x and the energy equation, will be simplified as follows. Try to see in your spare time that what all simplifications have actually taken place by comparing these equations with the more general form of the compressible transformed boundary layer equations. And why is it that for a flat plate in specific these simplifications were possible? So, if you do that homework exercise, you will get a better understanding of these equations. Again, we notice that these equations continue to show dependence on xi. There are several derivatives, for example, which are dependent on xi. And now we are going to explore whether the functions f and g are actually independent of xi or not. So, this is a query. So, if we were to substitute these forms, that f is just a function of eta, g is also purely a function of eta, instead of the forms which are existing into these two equations, there would be no more del xi terms left in them if in reality they are independent of xi. Now, you can clearly see that such a conjecture is indeed true, and that is an exciting result. The PDEs cease to have dependence on xi and they become ODEs. That means all dependence on xi drops out the moment you try to impose these functional forms there, which indeed means that f and g are not dependent on xi at all. Now, this leads to a huge simplification, because this is how we take the problem from a non-similar problem to a self-similar one, and in a mathematical sense the PDEs cease to have dependence on xi and therefore they become ODEs, because the problem is purely in the eta space instead of xi eta combination. So, now the derivatives are to be interpreted in the ordinary derivative sense, not in partial derivative sense. So, these are the x and x momentum equation and energy momentum equation, which are ODEs now. Now, in order to solve these equations, you will also need the boundary conditions, the compatible boundary conditions, both at the wall as well as the far field, that we have already learnt from our previous discussions. This is basically a 2-point boundary value problem, because you are satisfying boundary values on one end at the wall and at the other end at the edge of the boundary layer. The x momentum equation is a third order ODE, while the energy equation is a second order ODE. If you look at the equations, it will be very easily seen, and in terms of a numerical solution, you can look for a so called shooting technique using the Runge-Kutta integration, starting at the wall, that is eta equal to 0, and marching across the boundary layer thickness to large values of eta till the boundary conditions at the edge of the boundary layer are satisfied. Why do we call it a shooting technique? There is a reason behind it. We will explain soon. A total of 5 boundary conditions would need to be imposed at the wall. It basically comes from the order of your ODs, the 3 and the 2 coming from the 2 equations respectively. So, a total of 5, and that means at eta equal to 0 you will have to hunt for 5 of them. If you take an isothermal wall, then you have got 3 boundary conditions like what we have mentioned here below. So, in terms of the velocity field, the F0 and the F dash 0 are 0. In terms of the enthalpy, G is equal to GW. Now, you are left with 2 more to be satisfied and you do not know their values. Now, what are these 2 more boundary conditions? They are respectively F double dash and G dash, which are the ones of significant importance, as we have already said that they are linked to CF and CH or NU. Now, since you do not know them, you have to basically guess, and you guess by shooting at the target that you need to fulfill at the edge of the boundary layer, and thereby the name shooting technique. Based on the values that you guess, you can take some value between 0.5 to 1, for example, for both of those derivatives to begin with and iteratively rectify them. You try to shoot at your far field boundary condition by integrating the governing equations using a RK scheme, and then at large values of eta try to check whether you are able to fulfill the far field boundary values or not. If not, then from the error that you have made, try to rectify the F double dash 0 and G dash 0 values, and sooner or later you will be able to get your target right when you are shooting appropriately by taking the proper values of F double dash and G dash at the wall. So, the whole idea is again jotted down over here. Once you have got the converged values of F double dash and G dash at the wall, then you can get the correct values of CF and CH or NU at the walls. Now, for the flat plate, the transformed relation for CF will simplify a little further. That is also left as a homework problem for you to check for yourself, and you will find that it comes out to be like this. The local Reynolds number at a point on the flat plate is what is indicated using REX. This point is at a x distance downstream of the leading edge, and the interesting thing to compare it with is the Blasius solution. For incompressible flow over flat plate, the same CF was 0.664 by under root REX. The under root REX remains, but in the compressible case you have a complicated functional form like this. It can be shown that the compressible CF functionally also has a dependence on the similarity parameters, which can be expressed in this equation here in terms of a function. The under root REX remains in the denominator. The function in the numerator contains dependency on Mach number, Prandtl number, gamma, and the temperature ratio between wall and free stream. Coming to Stanton number, this is how it appears for flat plate. Again, comparing with the incompressible result, which has a dependence on Prandtl number as well, you see that the under root REX again shows up in the denominator of both, and similar to CF, here in case of CH2 we introduce a function F2 which shows its dependency on the similarity parameters. The Reynolds analogy, it links the CF and CH which are analogous in nature, the skin friction and the heat transfer coefficient, they are analogous in nature, and when you take a ratio, it nicely comes out to be half of Prandtl number raised to minus 2/3 for incompressible flow, whereas for compressible flow you have the ratio of these functions F2 by F1, which will of course be dependent on Mach number, Prandtl number, gamma, and temperature ratio, the Reynolds number under root will drop out. Concluding what we covered in this lecture, we looked at the transformed 2D laminar compressible boundary layer equations, especially the energy equation. We discussed about skin friction coefficient and heat transfer coefficient. We introduced Nusselt number and Stanton number. Simplification of the transformed compressible laminar boundary layer equations for flat plate was done. We discussed about the self similar solution, and comparison with incompressible flow Blasius solution was also done, and we ended with a brief mention about Reynolds analogy. Thank you.